Hey, what's up, guys? This is Chung here. So today, let's take a look at today's daily challenge problem number 581. Shortest unsorted continuous subarray. So this one is a very interesting problem. So basically, you're given like an integer array and nums here, and you need to find one continuous subarray that you only sort this subarray in ascending orders, and after that, you will have the whole array be assorted in ascending order. You need to return the shortest subarray in this case, right? So for example, we have this kind of array here, so the answer is this. So we need to sort from this one to here. Basically, after sorting this subarray here, we'll have like a sorted array in total. That's why the answer is 5 in this case. And in example 2 here, right? So since it's already sorted, obviously we don't need to do any sorting. That's why it's 0. Okay, and then this one is also 1, right? So with this 1 here, we also need to do a 0. Cool. So yeah, and here's the constraints, right? So there are many ways to solve this problem, but I think today I'll just introduce like two very common solutions. So basically, I think the very one very easy solution is that we sort these numbers. Basically, so for example, if we have like this kind of 2, 4, 2, 6, 4, 8, 10, 9, 15, right? So if we sort this array, so we'll get basically 2, 4, 6, 8, 9, 10, and 15, right? Uh, yeah. So, and we just need to compare. Basically, we just need to find the the lower bound. Basically, the leftmost number who is not in the right position, and then the rightmost not a number who is not in the right position. So in this case, we can see the leftmost one is 4, right? And then the rightmost one is 10. And we just need to find the distance between those two indices. In this case, is 5, right? That's how we get 5, right? I think it kind of makes sense, right? So basically, as long as we can find the leftmost misplaced numbers and then the rightmost misplaced numbers, so the arrays in between those two indexes are the subarray we need to sort. And obviously, this kind of time complexity is n log n, right? Because we need to sort this array. That's when we need n log n, and then we need to loop through the array to find the leftmost unmatched number and the rightmost unmatched number. Okay. Oh, by the way, so to find this leftmost and rightmost unmatched indexes, I think we can just loop through the entire array and we compare them numbers one by one. As long as the number is different, and then we update both the minimum and the maximum indices, right? That's how we maintain that. Cool. So, I mean, that's basically the first solution. And can we improve that? Basically, can we get rid of the sortings here? So the answer is yes. So with the similar like idea here, right? If we can find the leftmost, basically the mismatched and number and the rightmost mismatched number without sortings, that will be ideal, right? That will be a O of n time complexity. Yeah. So how can we find that, right? I mean, basically we cannot sort. We cannot rely on this sorted array here anymore, right? So we only have this one here. So how can we find that? If we know I think to find the rightmost one is pretty obvious, right? I think we just need a loop through the entire array here. Every time when we see like the current indexes, the current number is smaller than the previous one, right? And then we know this one is a wrong, is mismatched, right? Then we just update the basically basically I have a left and a right, and we can just update this right, and until once we have processed the entire array here, you know what's left in this stores in this right pointer will be the rightmost mismatched number here. But there's like some like another some scenarios we also need to consider. In this case, you know, we have 648, right? So how about this one? What if we have this one 643 in this case, right? So if that's the case, let's say if we have two consecutive numbers, right? That's who's smaller than the previous one. So assuming we don't have anything on this side. So in this case, I mean, the rightmost mismatched number is actually uh, it could be, in this case it's 3, right? And we cannot simply compare the current one with the previous one and to vary as a condition to check if this current one is a mismatched one, because there could be another scenario. Let's say we have 644, right? So in this case, the uh, basically still the rightmost mismatched number is this one. Okay, but if we only comparing the current one with the previous one, in this case they are the same, right? So if they're the same, we cannot tell if this one is a mismatch or the mismatched one or not, which means that we have to store uh the the first number uh so that, you know, every time when we have like as long as the current number is smaller than the very beginning one, than the start number here, so we always need to update the basically the right pointer here, and until we have see a different one. Basically, you know, now we have, since 4 is smaller than 6, right? That's why, you know, so the r will be here at the beginning, right? And then we move to here. So this 4 is also smaller than 6. That's why the r will be moved to here. So we'll keep updating r here until we have seen a bigger number, which is a number which is bigger than 6. Let's say we have 6 in this case, right? Or we have 8 in this case. So now the the right is will be pointing to here, since the 8 is greater than 6, and then the basically I'm going to have like current maximum. So the current maximum from 6 will become to 8 in this case, right? So now it's 6, and then we have 10, right? So now we have 10. So 10 is greater than 8. That's why, you know, we are gonna update this one from 8 to 10. And now we have 9, right? So 9 is smaller than the current max. That's why we're gonna update this r to here. So now the r, this is r here. Okay, and then we have 15 here, right? So the 15 is greater than 10, right? That's why we will not update r. So after this one, as you guys can see here, so the rightmost mismatched number will be this r here, which is 9. And that's how we can just use this current, maintain like a current max variables to update these are the rightmost unmatched indexes here. So how about the left one, right? So to get the leftmost one, it's quite similar as this the rightmost one. The only difference is that we have to traverse from the end to the beginning, and also instead of a current max here, we need to maintain like current minimum in this case, because, you know, actually similar like what we're trying to see, find like ascending orders from left to right. So when we try to find the leftmost mismatched numbers here, we're trying to maintain like a decreasing order from right to left, right? And then we use a similar logic, right, to track these things. But instead, this time, like I said, we have to maintain like a current minimum, right? So for example, I'll give you another examples here. Maybe I can help you understand that the second scenario here, second loop here. So let's say we have 1, 3, 4, 5, 2. So this is like shorter one, right? So if we do a left to right loop here, based on this rule here, we'll have like the rightmost index pointing to here, right? That's gonna be the rightmost pointer. So by looking at this kind of array by simply through our eyes here, we know that the left pointer, the leftmost mismatched pointer should be here. But how can we do it, right? So like I said, we also need to maintain like a current minimum from right to left, from the end to the beginning, which means that we're always trying to maintain like the decreasing order. Whenever we see a number which is greater than the current minimum, we know that okay, we need to update this left. So in this case, at the beginning, the current minimum will equals to 2, right? So now the next one is 5. So since 5 is greater than 2, right? So we'll update this one, update this 5 with L, right? So basically this L will become to this index where 0, 1, 2, 3 will become to index 3 here. Okay, and the 4 is also greater than 2, right? So that's why the index from 2 will become from to 3 will become to 2. That's this index, right? And then 3 is also greater than 2. That's why the index will be 1. But now we are at 1. So 1 is smaller, 1 is not greater than 2, which means that, we can reset this current minimum to 1, right? Yeah, similarly, like what we did for the current max. And with this kind of two for loops here, we can easily find the leftmost and the rightmost index we want to do the sort. And in the end, we simply do a right minus left plus 1, right? Because this is like the length. Cool. So that's pretty much the basic idea here, So to the implementation, it's actually pretty short in the after figuring out that pattern here. So like I said, so we're gonna have a current max. So at the beginning, it's gonna be a num 0, right? And then for the right pointers, we start from I'll just assign it to 0. So for I in range of 1 to n, right? So if the nums I, right, is smaller than the current max, then we're gonna update this right pointer with current I, right? Else we update this current max, right? Because we have find a better a bit basically we have find the like a bigger value, right, than the current max. So which means that we are outside of that unsorted range, right? Because as long as the current one is still smaller than as long as the nums I is smaller than the current max here, basically this if means that we're still in that range of unsorted array here, right? Which means we have 2, 6, 4, 4, 3, 3, right? So as long as the current one is smaller, still smaller than the current max, we know we're still in the range of the unsorted range. That's why we just need to keep updating it until we have seen a bigger one. That's when we can just stop updates current max. Okay. So similarly for the left boundary, right? We need to do a current minimum with the num start starting with -1, right? Since we're going to loop through from the end. So similarly, L is going to be 0 for I in range of n minus 2, right? -1, -1. So now we need to check if the current nums I is greater than the current minimum, which means that we are in that range of unsorted array from right to left as a descending order, right? And then we need to update left equals to I here. Else, similarly, we update the current minimum with the current numbers, right? And then in the end, we can simply return the L minus left plus 1. If L does not equal to R, right? Else 0, because for example, in this case, right? In this case, that both L and R, there will be a 0, R equal to 0. In this case, if we do this one, instead of 0, we'll get 1. That's why we do this check here. Okay, so if I run the code here, accept it. Yeah, so passed. So as you guys can see, this one is pretty fast because this is clearly a two loop here, and it's gonna be a O of n time complexity, right? Comparing to the sorting one, so this one is better, yeah, and it's pretty clear, right? We just need to do a two loop here, and yeah, the basic idea here, we just need to find the leftmost and the rightmost mismatched, misplaced number, and that's it. Cool. I think I would stop here, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.